Hello there, I'm going to continue the series on assembly programming. So last time we got set up with a Debian Linux operating system running within Docker if you're on a Mac computer or a Windows computer. But if you use a Linux computer already, then you can install NASAM yourself. NASAM is the assembler that we're using for this series. We got that set up, and we got Docker. For me, I'm using Mac OS 10, so I got a Debian Linux running within Docker on my Mac. And the way I can start that instance is by using a Docker command like docker run it, means run a shell within it. And I'm gonna map a directory, my home directory, in the /home. And then finally, I specify the name of the container, which I created a public Docker image, which you can also use for this purpose. And then finally, I can write the bash shell as the command I want to execute. If I write all of that, then I get this this shell which is running inside Debian Linux now. And this is to map a drive so that if I cd into the /home, then this /home mirrors what I have within my home directory. And then within my home directory, I have a playground directory. And within that, I have a lot of playground projects. The one I'm going to use, I'm actually going to make a new directory. I'm going to make directory, let's call it ASM Tutor, because asmtutor.com is the site I'm going to be pulling some lessons from. However, before I start getting into the lesson, I'm going to take this line and pull it out into my bash profile so that I don't have to write this very, very long line every time I want to do this. I actually have already done this. I created an alias, and the name of the alias is Debian, and I've set the result of the alias to this long command that I just wrote. And then, so you can add this syntax here into your .bash profile file. Save it, and to save it, you do Control-O to write out. And then you can re-execute this file by typing dot and then the path to your bash profile file, and then you have this alias set up. So now I can just type Debian, and then I'm into the shell. Wow, look how fast that was. Now there's the shell, and again, if you exit it, it just sort of cleaned up everything. Not the entire container, the entire instance of that mini computer has been blown away and teared up into smithereens. So the only reason we're able to perceive our work while we're in the Debian instance is because of the map drive. So I need to make sure all of the work I'm doing, I want to do it inside the map drive, which is /home. And then I'm going to again go into my playground directory and ASM Tutor to do my work in here, so that my work is preserved because it's mapped to my actual Mac computer whenever I write files into this directory. One more thing I'm going to do is to set the PS1 variable so that I can have a shorter shell. So my shell is just $1, and that's what I prefer because I don't prefer long shells. Okay, so now I'm in this directory that I just created, and it has nothing in it. And now let's write some assembly code. Let's go for lesson 1. Let's read this. So assembly language is bare bones. The only interface the programmer has above the actual hardware is the kernel itself. In order to build useful programs in assembly, we need to use the Linux system calls provided by the kernel. So in the environment of a Linux operating system, when we're making system calls, what's a system call? A system call is sort of like an API function, API provided by the operating system. And when they say kernel, really that's just the core of the operating system. So you can think of kernel as the same thing as operating system for most cases. So when you're making a system call, you're calling into an API of the operating system. And you can take a look at, there's a table here that it links to here that shows you a table of all the system calls that Linux has. And in the Hello World example, we're going to be using syswrite, which is to write something into the terminal, and we're going to be using sysexit just to exit the program, because just to exit a program you need to make a system call. So we'll do that. And let's write our program. There are these registers which will may kind of freak you out at the beginning, but these registers, you can think of them as variables inside of a CPU. You can think of a CPU as this programmer or this program. So like last time we said a CPU, it kind of looks like this. And you can think of it as, well, inside the CPU, there's this arithmetic unit, I think it's called the ARU, which does the calculations like add, subtract, multiply, and divide, and other stuff like that. But in order to do that, it has to get the inputs fed into it, and then its output, it has, after it computes something, it has to turn out an output which also has to go somewhere, and those values are gonna come either from or to these things called registers, maybe R1, R2, but they don't have names like R1, R2. Instead they have names like EDX, ECX, EBX, and so forth. And there are more of them, so these are some of them. So these guys will store values. You can think of them as variables that are in the CPU. And if you want the sort of calculator, the arithmetic unit, ARU, to calculate something, you need to load some values into these registers first, and then ask this ARU to do the computation based on the values that are stored in certain registers. And then once it's done the calculation, it'll get the computed value and store it into another one of your registers. So that's how things work. That's how things work with computation, but that's also how things work with syscalls. So with syscalls, you are telling Linux the arguments that you're passing to the syscall. You're putting in them in these registers, and then once you've loaded them up with the values that you want, you're gonna tell Linux, hey, can you do this system call for me? And it'll look at the values inside the register you put in to do the appropriate system call based on those values. So that's what we're gonna do. So let's write this little Hello World program as is. I'm gonna type it in, and you can type it in as well. Of course, you don't have to look at me type it in. You can go to the asimtutor.com website to look at the code there. But I'm gonna type it in front of you. I'm gonna use nano, and since they use the file name he used is helloworld.asm, I will follow that. I'm not gonna bother typing in his comments. I'm just gonna, like, these are comments. The words that come after the semicolon, those are comments, and I'm not gonna bother typing those in. Okay, so it's the data section is a place where you can store string literals and other literals. They could also be numeric literals too. This is saying we're gonna make a MSG constant. This, you can name this guy whatever you want. You can call it poop. But let's call it message. So, and you can use tabs or spaces, doesn't matter, to separate this one from DB. DB means, I forget what DB means, but it just means some data here. And then here's the string literal. This O8H, the H is actually special code that means hexadecimal. If you don't put the H here, oops. If you don't put the H here, then it's interpreted as decimal numbers. And OAH, the hexadecimal number of OA is actually 10. And if you are not good at converting hexadecimal numbers to decimal numbers in your head, you can use this online Hex Calculator. And okay, and you can type in, oh, what is OA, man? It'll calculate for you and tell you that's 10. So this OAH is actually equivalent to writing 10. And that's fine. I'm gonna write 10. And what the heck is 10? 10 is actually the ASCII code for the new line character. So if you go to ASCIItable.com, it'll show you all of the ASCII codes, and it'll tell you that decimal number 10, that's code for a new line. That in JavaScript that would be /n, but in assembly language that's the number 10. Okay, so now let's do the next section. The text section, in low-level programming speak, text means the actual program, so that's what we'll do. And the underscore start is the entry point of the program, and you have to name it that for some reason for the ASM, for the NASM compiler. Okay, so, and if you're familiar with C programming at all, in C this would be called main, but in NASM this is called underscore start. So now we're gonna actually write the first line of our code. There's 5 lines in this program, these move statements. Okay, what are these lines? Okay, so first, line number 1. Let's move the value of 13 into the register EDX. Remember, we have a CPU. It looks like that. We have a CPU, looks like that, and inside of it, it's got these registers, and one of them is called EDX. Well, let me make more room here. So I have an EDX register, which is able to store information in it. And this instruction is that, can you move the value 13 into the EDX register? So that's what that would do. Okay. And then line number 2 is, well, we have another register that's called ECX. And somewhere in the memory chip, what does the memory chip look like? Memory chip maybe looks something like this. Okay, so this is the memory chip, or RAM, random access memory. So we actually, or NASM has taken care to store this hello world exclamation point and then a 10, which stands for new line, somewhere in there. So somewhere in this memory chip, there's this hello world string in there. Blah, blah, blah. And this is saying, hey, wherever you stored this guy on the memory chip, can you take that address value? The address value is some number. I don't know 123. I don't know. It's a number that addresses this spot inside the memory chip, and he said, can you just take that number and store it in this ECX register? So if the computer runs this instruction, it'll put that number in here. And then the next one is doing the same with the EBX register. So we have EBX, and this is going to put a 1 in there. And then there's another register called EAX, and this is going to put 4 in there. And then we're going to trigger this interrupt. Interrupt is saying interrupt the flow of this program and send this number 80 in hexadecimal. What is the number 80 in hexadecimal? Let's see. 80 in hexadecimal, calculate that. It's 128. So this would have been equivalent to writing 128, and this program would be equivalent. But sending an interrupt is gonna sort of temporarily pause this program and then ask the operating system to get involved. And in this case, it's Linux. And Linux is gonna come in and look at the contents of these 4 registers and then determine what it needs to do. And in this case, because we're dealing with Linux here, it's going to base, and this reference will actually tell you what registers Linux is looking into. And so this kind of matches up. It says, oh, Linux is going to take the number from the EAX register to determine which of these system calls to actually execute. In this case, because EAX has the number 4 in it, that corresponds to this 4, and therefore it's gonna make the syswrite system call. So Linux is preparing to make this syswrite call. And syswrite is actually a function call with 3 parameters. And this contract basically tells you in order to get, well, it's going to have an FD, it's going to have a buff, and it's going to have a count. And it's basically saying, I need to get this information from the other 3 registers. I'm going to get the FD information from EBX. What's in EBX? Oh, 1. So FD is going to be 1. Buff, I'm going to get buff from ECX. That's this guy. So the buff is going to be 1, 2, 3, 4, 5. And then I'm going to get the value of count from EDX. It's 13. So count is 13. So basically the operating system kernel is making a call to syswrite with these guys as the argument values. What do they mean? Well, FD is the file descriptor, and it's like if you open a file, you get a number, a unique ID for that particular opened file in the operating system. But the number 1 for file descriptors is special. That it's a special file handle that stands for standard out. And standard out is whenever you write a command line program, you just print something like console.log or printf if you're in C. It prints the stuff to this special file called standard out, which always has the file descriptor number of 1. So we're just printing something out essentially. Buff is the string data that the operating system is going to read from to get the string, and we have 1, 2, 3, 4, 5, which is the location here of the memory chip that's pointing to our hello world message, and with a new line here. So it's going to print that, and the count is how many character from that location to print. This is going to print, we've set the count to 13, that was set here. and that just happens to correspond to how many letters there are total, I believe, because this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13 is the new line. So it will also print the new line. Yeah, and so that is what completes the system call. Let's see that actually happen. So now I'm gonna save this file, and I'm going to compile this program using this command. Oh, not nano, but nasum with a -f. That means the format of the output. It wants it to be in the ELF format, which is the format that Linux uses for its binaries. And then I'm gonna use the linker called LD to take the file. Well, the first step generated this helloworld.o. So so this step actually created the helloworld.o, and then the second step will take this helloworld.o and then generate this file, which is now here. So we first start from here to generate this, and then take this and generate this. And now this hello world, we can do /hello world to run this program, and we get hello world, and then we get a segmentation fault. It's okay, it's expected. The creator of the tutorial, oh, I have to give him credit. Let me find his name. Unfortunately, I'm not able to locate the name of the author for awesometutor.com. If you know who he is, or if you are that person, please let me know, and I would like to give him or her credit for creating these tutorials. But anyway, so this segmentation fault is expected, and lesson 2 is actually going to teach us how to fix it. And the way to fix it is you need to actually make another system call to tell the operating system to allow you to gracefully exit. And that system call is sysexit, which is system call number 1. And then it takes one argument instead of 3, as was the case with syswrite. So sysexit takes just one argument, and it wants to be placed in EBX. And the error code in Unix has the convention of 0 meaning success, but 1 meaning failure. And there might be more than one code for failure, I don't know. But in our case, we just care to say that we return successfully. So now I'm gonna try to not even look at the tutorial and do this and try to do this correctly, because I just have to move some values into EAX and EBX, and then call the interrupt command, and that should be okay. So I want to place the value of 1 into EAX, and I want to place a value of 0 for the error code into EBX. And then I have to trigger this interrupt to tell the operating system to get involved. So I'm gonna save this. I'm gonna up arrow to get back the 2 compilation commands I had from before, that nasum one and then this load command. And now I'm gonna run my hello world, and I get a hello world without a segmentation fault. Now let me see. Yes, that's exactly what he did. And now we have a hello world program that does an error. So I'm going to conclude this video here. Hope you enjoyed it. I hope you also follow along and get some hands-on experience with this. And I hope to see you next time.